All right, we're going to be looking at experimental design in this video because you will be designing several experiments in biomed throughout the trimesters. First of all, what is an experiment? This is a research study. You are going to be testing the effect of one variable on another variable, and you want to control as many parts of the environment as you can so that you can prove that whatever two variables you're looking at really did affect each other. We would like our experiments to be reliable and valid. Reliability is important because that tells me that someone else can do your experiment, they can perform it the same way, and they should get the same results. If you can't, then your experiment really isn't very reliable. We also want experiments to be valid because scientists are trying to explain the world around us, and so we want our results to be able to describe a real-world problem or question. These are the 6 steps of the experimental design. We're going to be going through each one of these in future slides. So let us start with identifying the problem. This is the first step. So this is where you're going to state your question. Normally it would be actually in the form of a question, but there are times where a simple statement is fine, that you're just trying to answer the statement. In our case, we're going to be looking at an experiment about fertilizer. Does fertilizer make your plants grow larger than plants grown without? So you're looking at fertilizer, the growth of the plant, does it help to have the fertilizer or not? And this is what you're going to be looking at in your experiment and trying to answer that question. Step number 2 is formulating a hypothesis. So you want to have a clear prediction. What do you think is going to be the answer? And in your hypothesis, you should always have an independent and a dependent variable, and you should state what those variables are. Now, if you aren't sure what an independent and dependent variable are, let's spend a moment and talk about these two. The independent variable is what you're controlling. So this is what you're manipulating as the researcher. What have you decided to do your experiment on? And the dependent variable are going to be the results you're getting, your outcomes, probably what you're putting in your data table. It's going to have to be measurable, so a lot of the times you'll see your dependent variable as you're recording it to be numbers, but it can just be observations, visual, any of your 5 senses, you can be using those as pieces of data as well. With your independent and dependent variable, it's usually about cause and effect. So if or does this particular item cause, affect, or change something else? When it comes to our fertilizer, we would be looking at the fact that we are testing as scientists fertilizer. So we would want to make sure that fertilizer is part of our hypothesis. And we wanted to know how it affected the growth. So we have to state the dependent variable is the plant growth. You and I can't control that. It's going to be based off of whether or not they had fertilizer or not. So that would be your dependent variable. So an example hypothesis might be that you think that the fertilizer will grow larger. The plants with fertilizer are going to grow larger than the plants not treated. Normally you might have an if and then statement, so you could write it as something like, if fertilizer is added to plants, then the plants will grow larger than those not treated. So you could put it as an if and then statement. I know many scientists would expect an if and then. In this class you're going to have a second sentence, and your second sentence is going to be where you are giving me your independent and dependent variable. So you're just going to flat out say the independent variable is this and the dependent variable is that. Step 3 is to design your procedure. And a procedure is where you get to your step-by-step details. So if you think back to the labs we just finished, you had to look at hair and fingerprints and blood and so on in these different stations. Every single one of them had step-by-step instructions for you to follow. Those details are important because if you skip over a step, you don't get some information copied down. So it's important when you're thinking through your procedures that you really do reread those and does it make sense? Can you go from step 1 to step 2, or did you forget to tell them to do something in between? Many times the procedure steps are where people have to go do some rewrites because it's really hard sometimes to write out step-by-step instructions. It's easy to leave something out and then things just don't quite make sense. Your procedure should also include the following items. Somewhere in there you're going to want to list safety concerns. What do we need to be careful of? For instance, with fertilizer, you'd want to make sure that nobody gets fertilizer in their eyes or whatever, those types of things. What should they do if they do? Materials, so you're going to list your materials. And you might have like a materials list when you're typing this up. So you could have materials ... and then list your materials. But when it comes to the main chunk of your procedure steps, those are going to be 1, you do this, 2, you do this, 3, you do this, and so on. So you could have, somewhere with your materials, safety concerns, control group, which we'll talk about in a moment. Any environmental conditions that need to be consistent. So with plants, you'd want to make sure they're both getting the same amount of sun and water. Other things that plants also need. So those are some things to keep in mind that you need to add into your procedure. You also want to make sure that in the procedure you tell them when to collect the data. So are we recording the height of the plant once a day, once a week, every other week, once a month? They need to know that. And then how many trials are they going to perform? Are they just going to do this once? When they're finished, are they expected to do it again? Okay, in all of our experiments, I'm going to expect these bottom 2 to also be in there. How are you collecting your data, and how many trials are you going to do? Now, a control group is the group that doesn't have the independent variable added onto it. So the independent variable being tested is not applied. And the reason that we do that is we want to be able to compare. Okay, we need a comparison. Things that had, for instance, the fertilizer, and things that did not have the fertilizer, so that we can compare, did the fertilizer really make a difference, or maybe the plants that didn't have fertilizer grew better without it. So we need to have a control group in every single one of our experiments. Positive and negative controls will pop up in certain experiments in this class. You may have dealt with them maybe in other classes. And we will talk about positive and negative controls when we get to some other labs, but for right now I'm going to kind of pass over that. And you can look through this. This Scientist 1 and Scientist 2 have done absolutely everything the same except for right here at the bottom. Scientist 1 gave every plant the same amount of fertilizer. All 10 of the plants got fertilizer and they got the same amount. But Scientist 2 took 5 plants and gave them fertilizer, the same amount, and 5 plants with no fertilizer. This is the control. This one has a control because you're taking your independent variable of fertilizer and you're not applying it to some of your plants. Scientist 1 does not have a control. So here are the results. Scientist 1 saw 40 inches of growth on each of their plants, and that's pretty good, 40 inches of growth. So of course the fertilizer made the plants grow. Scientist 2, on the other hand, because they have a comparison, they can see that they also got about 40 inches, 39 inches of growth. So we have some similar results. But the 5 plants that didn't have any fertilizer saw 41 inches of growth. So if you're doing a control, you can easily compare these. And if your hypothesis is that the fertilizer is going to make the plants grow better or taller, you see that that's not the case because you have something to compare it to. So a control is absolutely necessary. Step number 4 is to actually carry out your experiment. So you're going to follow your own procedure steps. You're going to collect the data into the data tables that you create. You're also going to record any observations. So maybe you have some visual observations that you're recording. So all of that's going to get carried out. And then once you have finished your experiment, you need to analyze your data. And your data is going to be put into the data table that you've told them to collect their information in. But we're also going to be creating some type of a graph with it. It could be a line graph or a bar graph. Different graphs are used at different times. In a line graph, though, or bar graph, your independent variable always goes at the bottom. So for our independent variable, we might have all 10 of our plants that scientist number 2 had, and 1 through 5 had no fertilizer. There we go. And 6 let's try this again. And the other plants, 6 through 10, are going to have fertilizer. So no fertilizer, these do have fertilizer, and we would maybe do a bar graph where we record how high, because our dependent variable was growth. So we would want to record the height of each plant and put that maybe into a bar graph so we can compare the bars and see which one had the higher growth. All of your data should be very clear, so this is why we'll use Excel to make graphs so that they're nice and neat. We can put good titles on them, have an X and a Y axis that's labeled, and it'll just be a little bit neater than if we hand draw them. And the last step that we would have in any type of design is to draw a conclusion, so that you have to go back to your original hypothesis. We said that fertilizer was going to make the plants grow. And if we look back at our data, we're going to see that our hypothesis was incorrect. And our rationale being that the plants with fertilizer actually had an average of 2 inches less. We had 39 inches with fertilizer, 41 without. So your hypothesis, whatever your hypothesis was, correct or incorrect, notice this ... you have to include some data here so that you can rationalize why you're saying it's correct or why it's incorrect. It always comes back to the data and what the data shows us. There are some other things that you can do when you're done. Depending on time, change your hypothesis and try it again. Maybe you redesign some type of flaw that you found. You could always come up with a new question somewhere in the middle and decide to run a new experiment, or maybe move on to a completely different topic. And depending on time in here, we may or may not have time during some labs to redo things, and sometimes we will. So it'll just kind of depend.